We have defined molecular orbitals. As you remember, an orbital is a one electron wave function. So, a molecular orbital would be the wave function of a molecule with one electron, and the simple one electron molecule that we have discussed so far is H2 plus. Now, what do we do with these orbitals? Of course, we do not want to talk about H2 plus and then go home. We want to talk about H2 and other more complicated molecules, do not we? So, today we are going to learn how to use these molecular orbitals to understand the bonding of homonuclear diatomic molecules. We will discuss hydrogen molecule, dihydrogen, and then we will quickly go through well, helium 2, does it form? We will ask that question, and then we will go through the second row, homonuclear diatomic molecules in this class. So, just to remind you, for H2 molecule, the first system that we want to talk today, under Born-Oppenheimer approximation, we have already written that this big expression for the Hamiltonian simplifies somewhat, because well, sorry, I did not realize I do not have the because here. This capital R is a constant, that is what we take. So, for every value of R, we have to work out these this Schrodinger equation using this Hamiltonian if possible, and the complicating factor is that R12 is not a constant. So, the moment you have 2 electrons, it cannot be solved. So, we have learned how to use linear combination of atomic orbitals to generate these molecular orbitals. You might remember that we can generate any wave function by taking an appropriate linear combination, and things become simple if we take linear combination of an orthonormal set, functions belonging to an orthonormal set. That is the general case. The special case we are using now is we are using this orthonormal set of atomic wave function, linear combination of atomic orbitals. By them we generate the molecular orbitals, and of course, we can use variation theorem and minimize energy, that will be the upper bound of the energy that we can hope to get, and then we fill in the electrons. That is the strategy for molecules, real molecules beyond H2 plus. Now, we have already discussed valence bond theory, and in valence bond theory what we said is that you do not have to restrict yourself to covalent bond. You can also include ionic terms by considering this kind of resonance and realizing that these ionic terms have to be scaled down. Their contribution cannot be too much, because in H2 you do not really expect it to be H plus and H minus to a very great extent, but it is not as if it makes no contribution. As we have discussed, as we keep on correcting the wave function, even addition of ionic contributions takes the energy down from 365 kilojoule per mole to 388 kilojoule per mole, whereas the experimentally observed value is 458 kilojoule per mole, which is as good as it gets. So, these ionic terms, please remember, can be brought in as an afterthought in valence bond theory by adding an appropriate term with that is appropriately scaled down. As we will see, in molecular orbital theory it arises naturally. Is it good or is that bad? Well, perhaps it is good as well as bad, but let us wait for it to come. Now see, so for molecular orbital theory of hydrogen, now we have moved on. We want to use molecular orbitals that we generated in H2 plus, and we want to describe dihydrogen H2 using those same molecular orbitals. Well, we might have to correct for shielding and all, that is fine, but assuming all that has been done and assuming that variation method has been used to minimize energy, the kind of expression we get is this. Your psi bonding would be 1 divided by root over 2 plus 2s, and I am sure you remember what s is the overlap integral. 1 by root over 2 plus 2s is the normalization constant of the plus combination phi 1s A plus phi 1s B. This is our bonding orbital, and we know what the anti-bonding orbital is as well. But for hydrogen, both the electrons would go into the bonding orbitals, because like atomic orbitals, molecular orbitals can also accommodate 2 electrons. So, we will place the second electron in the bonding orbital. Then what is the wave function that I am going to get? So, psi bonding of dihydrogen is going to be something like psi bonding occupied by 1 multiplied by psi bonding occupied by 2. Of course, we are going to expand this expression and see what we get. But well, here it is without much ado. Do you agree with me that this thing that we have written, this wave function, it is symmetric with respect to exchange? I hope you have not forgotten what we had learnt in while discussing many electron atoms. The total wave function, which is a product of spatial part and spin part, that wave function for a fermion like electron has to be antisymmetric with respect to exchange. So, what we have here is that we have a symmetric spatial part, right. You can just open it out. We are going to show you the result of opening out. It is very simple. So, since the spatial part is symmetric, it is not very difficult to understand that the spin part is going to be antisymmetric, alpha 1 beta 2 minus beta 1 alpha 2. So, what we learned right away is that the ground state of dihydrogen according to molecular orbital theory is a singlet state. Remember, the spin wave function is a unique one. In triplet you have 3 wave functions, right, alpha alpha, beta beta, alpha beta plus beta alpha. But alpha beta minus beta alpha is a unique wave function, a standalone wave function by itself, and that is what gives the singlet state. Singlet means there is only one state with that energy. And I hope you also recognize that this is the same result that we got in valence bond theory as well. In valence bond theory also we had worked out that the ground state of dihydrogen is going to be singlet. Remember, the ground state when energy went through a minimum, it was an associative state, whereas the triplet state that we got from valence bond theory turned out to be a dissociative state, it would never form. So, with that we can go ahead and complete our discussion. Let us expand the spatial part, this is what we get, and once again I am going fast because after all that we have learnt in this course, all this is child's play for you. One thing that I want to highlight is this. Okay, as usual we have written, instead of phi SA and all that, we have written 1 SA1, 1 SA2, etc., etc. See, just look at the first two, well, look at all the terms one by one. Start with the last. Last one is 1 is B1, 1 is A2. What does that mean? Electron number 1 is in atom B, electron number 2 is in atom A. So, exchange has taken place. Second last term, the third term is 1 is A1, 1 is B2. Electron number 1 in atom A, electron number 2 in atom B. Now look at the first two terms, 1 is A1, 1 is A2, 1 is B1, 1 is B2. What do these stand for? These stand for the situation where both the electrons number 1 and 2 reside on atom A or both the electrons reside on atom B. So, what kind of situation is that? H plus H minus. The atom which has both the electrons, that would be H minus at that instance, and the atom which has no electron now would be H plus, and I mean there will be resonance between all these forms. So, these are the ionic terms. And as you see right away, so good thing, what is a good thing about molecular orbital theory so far? Ionic terms have materialized by themselves. We did not have to think that they would be there and we did not have to invoke them. What is the bad thing? MOT has actually overdone it. Where is that lambda? Remember the lambda scaling factor that we used in valence bond theory, and we said that this lambda has a small value. So, ionic terms have a small contribution as might be expected. That lambda is not here. So, MOT is a general theory that well gets us the ionic terms, that is great. The problem is it overdoes it. Once in class I said that it in its enthusiasm to be very general, molecular orbital theory overdoes it. And the problem was somebody quoted me and wrote this in the exam. So, when we were correcting, everybody else correcting the scripts had a good laugh at my expense, because the student had written, according to Professor Anindya Datta, molecular orbital theory in its enthusiasm to be too general sometimes overdoes things. So, then I realized that I have also perhaps overdone, I have been too enthusiastic. So, I do not say that joke anymore, but well I have right now. Anyway, PJs apart, MOT as we see overemphasizes the ionic term. So, that is the problem. So, when you get MOT results, you need to keep an eye on them, right. Sometimes you might get little extra that is not really correct. Okay. So, now we know these well, constant probability surfaces of bonding orbital, anti-bonding orbital. For H2 both the electrons reside here and this would be the energy level diagram. Okay. Excellent. Now, if you fill in the electrons and make it say He2 plus He2, then what happens? Let us have a look at the numbers, and these are all calculated using variation method. So, H2 plus has a bond order of 0.5, that is not very difficult to understand, we know what bond order means. Bond length is 106 picometer. Binding energy in kilojoule per mole is 268. H2 bond order is 1 because 2 electrons are there in the bonding orbital, no electron in the anti-bonding orbital. Bond length is 74, which is not very far away from the reality. Binding energy turns out to be 457 kilojoule per mole. He2 plus bond order is again 0.5, very similar to H2 plus, but bond length is well more or less same 108, but a little longer, right. 108 is a little longer than 106. So, bond length for He2 plus is a little longer, little more than that of H2 plus. Also, if you look at binding energy, that is a little more, well, what am I saying, it is actually minus, right. So, He2 plus is not as stable as H2 plus, it is more unstable than H2 plus. Of course, both of them are more unstable than H2, that is a best case scenario, but the point is that He2 plus and H2 plus both have same bond order, but energies are not same. H2 plus actually has a little more stability than He2 plus. Why? Because in H2 plus you just have 1 electron in the bonding orbital. In He2 plus you have 2 electrons here and 1 electron here, and if you remember the picture that we had shown in the last lecture, this energy difference between the isolated atom and anti-bonding orbital is a little more than the energy difference between the bonding orbital and the atomic orbitals, okay, at equilibrium bond length. So, He2 plus is less stable than H2 plus. And what about He2? Well, bond order is 0, you do not even expect it to form, right. But if you look at this graph, there is something, is not it? There is a little shallow trough. All these are much bigger troughs. H2 is the deepest, followed by H2 plus, followed by He2 plus. He2 has a minimum for a bigger internuclear separation, much bigger, much larger, 6000 picometer, but there is a minimum, right. Binding energy is very small, much less than 1 kilojoule per mole, but it is there, it is not 0. Where has that come from? That has come from intermolecular interactions. You might have studied van der Waals interactions and all. Even separate molecules that are not bonded to each other, when they come close to each other, they can induce dipole moments in each other, right. So, this induced dipole interaction is what you see as the factor that causes a little bit of stabilization at very large internuclear separation of 6000 picometer for He2. Okay. So, that is first row. For second row, when we go there, we are not going to discuss this in too much of detail, because again we have been studying this since we were in class 11 or class 12. One thing that we need to remember, and I think we have used this term earlier, but now we bring it back, it is important that symmetry and energy both are matched. Symmetry and energy of the atomic orbitals would have to match in order for them to participate in the linear combination which gives rise to the molecular orbital, and we work with valence electrons. What are we saying here? This is H2, we have discussed already. There 1s and 1s, of course they have the same energy, and they have given you the picture we have discussed. If you talk about HF, and we will come back to it, what happens is as Z increases, stability of the orbitals increases also, they go down in energy. So, 1s orbital of fluorine is much lower in energy than 1s orbital of hydrogen. Their energies are not compatible, they do not form bond, they do not participate in the linear combination for forming molecular orbitals. However, the energy that is close, that also there is a difference, right, and we will talk about the implication of this difference in the next lecture, but the one that is closest is F2p. So, it is F2p that participates in linear combination with hydrogen atom 1s orbital to form the bonding and antibonding orbitals. Even then one needs to consider symmetry as well. See, let us say this is my 1s orbital from hydrogen. So, let us say this is z axis approach of direction of approach. This is Pz. Since color is free, let me use colors. This is Py. Okay, there is no meaning of this larger lobe of Py, it is just my poor artistic skills. And this is Px pointing towards us. Okay, I will make this a little fat and going away from us. Okay, this is Px. Now see, Px, Py and Pz all have the same energy, do not they? However, only Pz is in the right disposition to give you sigma interaction with hydrogen, or I will even say bonding interaction with hydrogen 1s orbital. Yeah, because this is plus, oh, I think I chose white as color, that is why there is a problem. So, this is plus, this is minus, let us say this is plus. What about Px or Py? This is 1s, let us say this is plus, and Px or Py would be like this, plus minus, that would be non-bonding, is not it? So, Px and Py would actually remain. So, if I draw this Px and Py here, they would remain as non-bonding orbitals. This is the meaning of non-bonding orbitals, orbitals which have either improper energy or improper symmetry to participate in bonding and antibonding interactions. They remain non-bonding orbitals and they remain property of one particular atom. Okay. And Pz forms these sigma and sigma star orbitals that we will talk about later. So, energies have to be close, symmetries have to be compatible, then only orbitals of two different atoms are going to participate in the linear combination and give rise to MO. This is a most important, it might sound to be very simple, but it is important nevertheless, we better understand it. Now, with that background, we can try to develop an energy scheme for second row homodiatomic molecules, and this is what the scheme would be. See, in multi-electron atoms, right. So, 2s and 2p would not have the same energy here. In hydrogen atom 2s and 2p all have the same energy, you might remember the energy expression has nothing in L, it is N all the way. So, here what will happen, 1s and 1s they close in energy and symmetries are same. So, you get 1 sigma star. Well, this 1, 2 these are just sequence in increasing order of energy. There are different ways of writing the names of these orbitals, I have used this convention. Then 2s and 2s give you 2 sigma star, 2pz 2pz 3 sigma star, and then 2py 2pz, in this case they will not remain antibonding, sorry they will not remain non-bonding, because this one has 2px 2py, this one also has 2px 2py, right. So, they are going to form pi orbital, pi MOs like this. This is 1 pi MO, this is 1 pi MO. Okay. Now, next thing to do is to fill in the electrons. When we do that, if you take this scheme that we have done already, sorry for the quality of these figures, they are xeroxed from I think Huey's inorganic chemistry book, but I think you understand what I am trying to say. So, if we use this scheme and fill in the electrons for dinitrogen, how many electrons are there in nitrogen? 2, 4, 5, 6, 7, right. And then you start distributing them 7 into 14 electrons, 2, 4, 6, 8, 10, 12, 14. So, what we see is that the HOMO highest occupied molecular orbital would be a pi orbital. But if that is the case, then nitrogen should have been very reactive. Remember, alkenes are prone to addition reaction, right. Remember bromine water test for unsaturation, you have alkene or alkyne, you add bromine water, it gets decolorized. Why? Because bromine adds and gives you dibromo derivative. If nitrogen indeed had pi orbitals, as the highest occupied molecular orbitals, then they would participate in addition reaction. Fortunately, that is not the case, because you remember what is the percentage of nitrogen in our atmosphere, in air, that is by far the biggest component. If it was very reactive, then everything would have rusted, everything would have perhaps caught fire, everything would have reacted away with nitrogen, and we will have a world or universe full of nitrides. Fortunately, that is not the case. Nitrogen is inert and it does not undergo addition reactions. That means this model that we have constructed is not right, we need a different model. And this different model is built keeping in mind that not all atoms or not all elements in the second row have to behave in the same way. So, we start from the situation of hydrogen. So, in hydrogen 2s and 2p orbitals are degenerate, right. Now, when in a many electron atom we said they are different, but then is it a 0-1 situation or is it gradual? Is it that for hydrogen you have this 2s and 2p orbitals that are of same energy and all of a sudden you go to second row and they become different in energy from the beginning, or is it that it is graded, that for the lighter elements for second row do we still have S and P close to energy, and since their energies are close, can they mix to form hybrid orbitals? And then as the atomic number increases, does this energy difference between 2s and 2p become more prominent, and does the model that we have proposed earlier become applicable? Okay? Let us see. So, for dinitrogen, if we invoke this model where we have sp mixing, again this picture is from Huey and I am not discussing too much in detail because I am sure all of you have seen this. In case of any doubt, feel free to contact us, the TAs or I will help you out. So, when we consider sp mixing, then the energy level changes. You have we will come to this, well you remember we talked about G and U in the last class. We have this bonding Z symmetric to inversion orbital followed by antibonding, but look at the lines here. This antibonding orbital has contribution from not only this 2s, not only this 2s of nitrogen, but also one of the 2p's, 2pz, one of the 2p's here, right, 2pz. So, these lines are drawn to indicate that sp mixing has taken place, and when that happens, energy levels do not follow that pattern that we had shown you earlier. What happens is this sigma bond, this sigma orbital, which you would expect to be lower than the pi orbital, comes above in energy. So, now HOMO that we get is actually a sigma orbital which would not undergo addition reaction. That is what makes dinitrogen so unreactive, and that is why one of the pioneers or perhaps the pioneer of modern chemistry in India, Acharya Prafulla Chandra Rai, he became famous because he could make dinitrogen react with mercury to get a nitride of mercury. Okay. In later time this claim has been disputed, and another eminent researcher also from India had said that P.C. Rai was wrong, it is not mercury, not nitride of mercury. But then yet another group got together and using X-ray crystallography showed that he was right, after all it is nitride. So, the reason why there was so much of fascination about formation of this nitride with mercury is that nitrogen is so unreactive because the HOMO is sigma. Okay. So, this modified energy scheme considering sp mixing nicely describes the situation for dinitrogen. Okay. So, what we are saying is that for small energy gap between 2s and 2p, that is for smaller z values in the second row, there will be mixing, and the scheme that you have is like this, As a BSc student I used to be fascinated by this diagram even before I read this. This is again from Hughes's book. It looks like a lunar orbiter, lunar lander, well I forgot the name right now, lunar module used by the first lunar expedition. It looks something like that, right. So, this is the scheme that is proposed involving sp mixing. Now, does it work only for nitrogen or for other things as well? Now, I will go through this quickly. B2 is known to be paramagnetic and that would only happen if you have energetics like this. See, if the sigma orbital would have been lower, then that would be HOMO and the electrons would be paired. Actually, paramagnetism indicates that the electrons are unpaired, which can only happen if the HOMO is a set of 2 degenerate orbitals, that is pi orbitals. So, this model of sp mixing nicely explains not only nitrogen, but also behavior of other molecules that would have appeared to be anomalous with smaller z. There are many where there would be no problem at all. I actually wanted to show you a very recent paper on B2, unfortunately I forgot it. If I remember, maybe in one of the next classes I will just flash it, but actually the moment is gone, I should have shown it now. There is a paper published on this as recently as 3 weeks ago in one of the most reputed journals of chemistry. This is from Indian Association for the Cultivation of Science. Professor Devasri Ghosh and Professor Ankon Pal have done some fantastic work on this homonuclear diatomic molecular orbital theory. I am saying this to indicate that it is not as if we are studying something that was worked out many years ago, it was, but it continues to remain relevant and enchanting. We will come back to this when we talk about carbon monoxide as well. Alright, for F2 there is no sp mixing and that is what we see experimentally. So, the energy scheme that is to be used is the other one. So, what we see is that if you go from lithium 2 to F2, it appears that first of all this energy lowering will be there, but this relative change in the relative ordering of energy of the sigma and pi orbital appears to take place between nitrogen and oxygen. If you ask me why, my honest answer will be I do not know. We are not saying that we know why it happens, we are just saying that the sp mixing model works nicely up to nitrogen, dinitrogen, and it is not manifested beyond dinitrogen, that is all. Oxygen for example, yeah, oxygen is paramagnetic, right. So, these are things that get explained by this interchange of sp mixing model to no sp mixing model between dinitrogen and dioxygen. So, that is all we wanted to discuss for homonuclear diatomics. In the next class we will discuss very briefly heteronuclear diatomics, and then again briefly we will talk about polyatomic molecules and we will see how symmetry plays a very important role in bonding of polyatomic molecules, and what we say is going to be only the tip of the iceberg.